All right, so those of you who are taking the class remotely will not hear all the fun, interesting trivia about what's the matter with you, but what's the matter for you. Okay, so today I think we're going to finish up some of the logic puzzles. The swiveling technology is not working, so I will try to stay somewhat localized. And we're talking about the egg drop problem. Do people want to do more discussions on egg drop, or do we want to move on to a new riddle? Okay, move on to new riddle. You're technically supposed to speak out loud and not nod your head, but I will say loudest head bob. All right, so there were three other logic problems I had put out for everybody to look at. After this, I thought we would segue into job interview problems. So job interview problems is a really good source of interesting mathematics. Now that I'm done with the art museum, I can turn off my phone. What's nice about job interview mathematics is not only is it fun mathematics, but it is mathematics that can help you get a job. So there are various websites that post interesting puzzles. You know, these are things that people have been asking in job interviews. So if any of you have been on a job interview and have some good problems you can share, please do so. If any of you want to just go online and look for a few of these so we can think about them ahead of time, that's great. If not, I'll just try to find a few myself, or I'll pull a few problems from the Virginia Tech. This is a great way to prepare for upcoming stuff. All right, so the other riddles we had was we had the light switch problem, we had the grid problem where you were moving things, and and we had the blue-eyed problem. Any preference?
Switch.
I'm sorry?
Light switch.
The light switch. Oh, okay. I was just saying switch topics and I was kind of okay, light switch. So this is the one that caused me the greatest difficulty in all the riddles that people have submitted to me to post on my webpage. The only way I finally got this was I walked 50 minutes from my wife's office back in Boston to our apartment, to our home in Brookline, and just no paper, no pens. Because all of these problems you should be able to solve elegantly. There's a clear way to look at them. If you look at them the right way, it's not hard. If you look at it almost any other way, it is mindlessly frustrating. Have I told you the story of the killer problems or the Jewish problems? And they changed the title for publication. Did I tell you guys the story?
No.
So these were problems that were used in the Soviet Union to prevent Jewish people from getting PhDs. And the purpose of these problems were they had to be extremely difficult, but they had to be very defensible. I don't understand, this is not that difficult, and so it always had to be very easy to explain the solution, but very hard to find the solution. And so if you go to the archive, if you Google either Jewish problems or killer problems, one of them should come up with a hit. All right, so the way the light switch problems works is I think there's 46 prisoners, or 23 prisoners? 23 prisoners, 2 light switches. That is switches. Switch is one of the words my son has to learn how to spell this week. 2 light switches enter room one at a time. All enter infinitely often, but unaware of the order of entry. So basically think of it as we have 23 jail cells. They're all isolated. And then one at a time, the prisoners are taken out of the jail cell and brought into this conference room where there are 2 light switches. And the prisoner must flip one of the 2 switches. When enter, must flip a switch. When one prisoner is sure all have entered room, says, free us, and they're all freed. Okay? This is not a class on social policy. I have no idea why the jail works this way and why they are putting prisoners into this conference room one at a time. And as soon as one prisoner is sure that every prisoner has seen the conference room, all the prisoners get to go free. These are the givens.
You guys see this conference room.
Do they get to decide on a strategy or talk to each
The prisoners get to, well, they were actually all Confederates, and they had a suspicion that they were going to be sent to this jail. And they came up with a strategy just in case this would happen. When we talk about planning ahead, now if they had spent more time planning about the actual heist, they might not have been in this situation, but at least they are now in a situation where they can take advantage of their plan. So they are mathematicians, they have a great plan, they're ready to implement and execute. So does everybody understand? Each prisoner is guaranteed, we almost have enough to do this game right now. Each prisoner is guaranteed to come into the room infinitely often, but you don't know when. I might decide, I really like seeing Jesse move, he's the TA, I can do this to him, he can't really complain too much, the rest of you. So I'm going to keep bringing Jesse in for the first 1 billion times. I can do that. Okay? So it could be an extremely long time before somebody else comes into the conference room. And I might decide, you know what, I really like having Jesse move, let me have Jesse move back another 1 trillion times. And then I bring in another person, and instead of 1 trillion, I'll do a quadrillion this time for Jesse. I can do that. Okay? So you have no idea how long of a wait there must be. All you know, yes.
Are there 2 different lights for the 2 different switches, or is it 2 lights to go like switch on the same light?
There's just 2 switches. We don't even know if the
there's
switches
no
do
light.
anything.
We don't know about.
They just have
Oh, okay, okay, cool.
And they say on and off, up and down, whatever you want. And the light switches can only be in 2 different positions. They can only be up or down. You can't do it in incremental amounts.
And do they like know the difference between the 2 switches?
They do know the difference between the 2 switches. So they know the 2 switches and they know if the switch is on or off. If you could move the switch an arbitrary amount, what would you do?
Just each of you move it 1/23 way, and then the rest of the time do the other one.
I'm sorry?
The first time you go in, move it 1/23 of the way, and then the next time you go in, move the other one.
Right, but then
You don't know which way it was.
you don't know how many people have gone in before you.
Yeah, but you only need
Yeah, you do. But it's just when
every
when one of them goes.
time just where you have the other ones. This one stays.
But they might be
So right now, for those of you at home who can't hear this, the suggestion was the first time you enter the room, you move one of the switches 1/23 of the way. And if you've already been in the room, you move the other switch. And it doesn't really matter what the other switch does. You know, the first switch, that's the good switch. That's the one we all care about. You know, we care about the switch on the right. This is the one that matters. This one, you know, if I have to move a switch, I'll move this one, but this is the one I desire to move. The problem is, yes,
Well, you don't know which orientation it starts,
you
right?
don't know which orientation it starts.
Can't you
No,
decide?
that would actually work because as soon as you found it, like, as soon as anybody found it just 1/23 away from, oh, actually no, because if one person, the first person came in.
Okay, so
Like,
we
you
might
wouldn't know
be
whether
able
you're
to we might be able to
1/23.
fix this because the problem is if it was initially started up and we move it down 1/23, the next person would know. But
Yeah, and furthermore, if you know you're the last person, if your move completes the orientation.
right, but you might not know which direction to be moving it.
Yeah.
Can't we just
Oh, but
decide
you
to
know,
start
once
it
you
off?
see it
In both orientations matter, you can just set it.
Okay, so we could always decide that the goal is to move the switch. The enemy's gate is down. Move the switch down.
But I just have a question.
Yes.
But if, say, like Jesse moved the switch 1/23 down, but then he leaves the room, and then another person comes in and like thinks he's in the room because the switch has moved 1/23 down, but he's actually not there. So it
Well, the
could.
problem is if Jesse moves it 1/23 down, if I come in now, how do I know that it's been moved 1/23 down as opposed to 22 people have moved it up?
Can't you just decide in your initial strategy that you're going to move it from off to on? And
Okay.
then if it was in the on position when you're the first person, oh, actually.
Oh, no, you're almost there. You're almost there.
The first person to go in moves it all the way down to 1/23 from off.
And then
Do you know
that
if you're the
person,
first?
I'm sorry?
Do you know
Oh,
if you're
yeah,
the first
that's
person?
hard.
You don't know if you're the first person?
Well, there's
you
always a
know
way
that,
around
like-
this.
Try and see it in both orientations.
So there's a way around this by
Okay.
having a different key position for the calling. So if you see the switch fully down, then that you don't call, you move it up. And then after that, the first time that you encounter it not down, you move it down 1/23 of the way. And then after that, you always move the second one. and then as soon as somebody encounters it 1/23 away from being fully down, they can declare.
But can we set up so that no,
That should always work because,
okay,
because the down
that might
position
work,
is an ambiguous.
that might work, write it up, I'm not,
All have been in the room. Okay,
That's
sorry.
like,
yes.
that's
Th-
assuming that you're,
That might work, I think there's a tweak on that that's much easier to state.
well, that is assuming that it has to start either up or down, and that the switch won't start anywhere between,
Right,
which could be an issue.
right.
If you have infinitely many trials, you could also wait until you've seen it all the way down and all the way up.
So you could do something like that. But you've got to be careful as you're going through, when you come, do you know if you're moving it down or moving it up? What I like is, what if we just say, if you see the switch all the way up, move it down? And then after that's, yes.
Never.
Yeah, like if you move, well, I guess if you are assuming that the way you can tell if it's the first time is that if you're the first person to go, you move like the left switch all the way up or down, indicating you've set the orientation now. And then you set it like 1/23 downwards. And this way, the second person who sees the orientation, right, will flip the switch again saying, I'm now going to continue this process and now you can keep going all the way down.
Okay.
Can you only flip one switch?
You can only flip one switch.
Could
How
you
many-
also just move in the same direction, right, and then you'd have cycles? So it doesn't matter where it starts, if like you say, we're always moving from off to on, and it doesn't matter where you come in like initially, if you just keep moving from off to on, if you go through one cycle.
So I mean, I think one of the things we want to extract from all this is that we're not necessarily trying to find the minimal time when everyone has been in the room once. We're trying to find a time when everyone has been in. So it's important to answer the question that is asked. In advanced analysis today, I was talking about one of my favorite methods of proof. So if you look at primes in arithmetic progression, say you want to show, is there prime P congruent to A mod M? What this means is that means P minus A is a multiple of M. Something must be true in order for this to have a chance of happening. If A and M share a common factor, then unless A is prime, there's no way this can happen. If A and M are relatively prime, it turns out there is always a prime congruent to A mod M. The only way we can prove this in general is the following. We prove that not only are there infinitely many primes congruent to A mod M, but that the primes fall evenly among the different residue classes modulo M. And therefore, since there are infinitely many, there must be one. If you've ever heard the expression killing an ant with an elephant gun, this is several orders of magnitude farther. This is the level of neutron bombs being dropped on the ant. This is extreme overkill. How do I prove that one exists? Well, I prove that there are infinitely many. And if there are infinitely many, there must be at least one. That's overkill. In this problem, which is beautifully written here, does it say find the first moment at which someone can declare everyone has been in the room? In problems like this, it's very easy to accidentally assume things that you're not supposed to be assuming. Here's one of my favorite riddles. It's tough to do this on the blackboard because normally, I'm just doing this with people. I'm on a table. Is everybody in the back able to see this? Did I go too low on the blackboard? Is this high enough? Okay. So the question is, I want to connect these 9 dots with 3 straight lines without ever picking my pencil off the paper. How many of you have seen this before? Okay, if you've seen this before, of course, please be quiet. This seems like it should be impossible. I go through these 3. If I come down like this, and I come over like this, or if I come like this, and this, I'm going to be missing 2. How can we go through these 3 dots, through these 9 dots with just 3 lines? Have you seen this before? Okay.
The lines don't have to be straight.
Lines have to be straight.
This is in Euclidean space now.
This is in Euclidean space.
Mhm.
I mean, this is really in Euclidean space. This is on the
They
blackboard.
don't have to have their endpoints as vertices.
No, No, you could start down here, you could start at an angle, you could start off going diagonally like that if you want, and then come down like this.
They don't have to be connected.
You can't take your pencil off the paper. So in the interest of time, I'll try to... So this is not, you're going down like this, and then you come back up like this. The idea is that these are not points. They're points. There's a difference between points and points. They're not no length, no width, no height. These have thickness. These have width. And because they have width, you can pass through them. And so the whole point of a problem like this is to get you to make subtle assumptions. So many of these riddles and so much of math research is about breaking the assumptions, is getting rid of the blinders. So in a problem like this, one of the things you're focused on is efficiency. I know I am. I'm teaching the class on that right before coming here. Do you think the prisoners enjoy being in their cells and being led one at a time to this conference room to flip the switches? No. Do you think they want to get out of this situation as fast as possible? Yes. But they also want to make sure they get out of it. And so the way it's phrased is I'm not asking for the first time that they are done. I'm just asking for a time when they're done. And so a lot of the things we were discussing is we don't necessarily know what the initial configuration was. So whenever you're doing a problem, and again, I don't want to jump to the solution. I want to just discuss how you should be thinking about problems like this, or how you might think about problems like this. If there's an obstruction, try to make it work for you. What would be a wonderful fact to know?
Sorry.
The starting position. Anything else you want to know?
First guy.
The first guy. So sometimes it actually helps you to make additional assumptions and see, hey, can I do it in that case? Sometimes additional assumptions are dangerous because they have you focusing on things that don't really matter. Did we talk about the transcendence of e plus pi versus e times pi? And so it might make you think that e to the I pi is important. It's not. Sometimes it does help to try to think of special cases. Well, what if I knew the initial positions? What if I knew who was in first? Would I have a strategy in that case? So what would be your strategy? We're going to keep using Jesse as the TA. Jesse will be first, and he will get to see the initial configuration. You know you're first. What should we do now? Yes?
I mean, he switches it to a definite position.
So he switches it to definite. If he finds it on, he switches the switch to off. And now what's the rule for everybody else? If you ever see it in the off position, move it up. If you see it in the on position, what do?
You leave it.
Don't touch
Say,
it.
free us.
Is that going to work? How many times are you allowed to move it up? Once. So imagine you're not Jesse. That should be easy for most of you. Okay? So you're not Jesse, you walk in. Jesse initially saw it was, did you see it was up and you moved it down? Let's write down to
It was a long time ago.
It was a long time ago. I mean, you've been doing this for so long. All right, so stop. Jesse sees, well, watch it.
Can we see it off?
Sees
Start off.
Sure, sees the key switch is off.
And if you say free us too soon, does everyone die?
I'm sorry? Yes,
Oh.
horribly.
Just keep saying it.
You watch marathons of Punky Brewster and the best of Jar Jar Binks. So, flips it on. Then, if enter, and it's the first time you see that switch on, you move off. And otherwise, you just flip the other switch. All right, so Jesse comes in, he sees it was off, he flips it on. And then everybody else, if you come in, if it's the first time you see the switch is on, you pull it down. Otherwise, you just play with the second switch. and you will only do this once. So this is a way to count every time a new person has entered the room. Now the problem is, let's say Jesse flips it on, and then Jesse leaves. I come on, and I flip it off. And then Jesse comes back and he flips it up. I come back in. Do I do anything?
Wait, why does Jesse flip it on again?
Oh,
He's counting. We
Jesse's
say that
counting.
every
Oh,
single
Jesse's
time.
counting.
Yeah.
Jesse's counting.
So is that just setting it for something?
So Jesse's gonna say free us.
Right, Jesse's
Yeah.
good, Jesse is, yes. In the words of the Lego movie, Jesse's the special.
So then once I've had to flip it down 22 times,
So once you've had to flip it down 22 times, you'll know, well, not 22 times, I think 23 times?
yeah, well, including the first
Because
time.
including the first time. Then we'll have counted.
What if he forgets?
Then we have to really think about our screening process for TAs. I mean, we went through a really rigorous process, such as, will anybody TA this course, please? And so, will this work? Is there ever a danger of somebody flipping the switch twice? No, because I can only flip it once if I'm not Jesse. If I see the switch is off, I'm not allowed to flip it up. I only move it from up to down. And so because we know everybody comes in the room infinitely often, we know Jesse will be in the room at least twice. Well, that's not enough. We know he'll be in at least 3 times. We know he will be in it after everybody has been in the room at least once. Right? That's the key fact. Because everybody's been in it infinitely often, there's not an infinite wait between when somebody comes in and when Jesse comes in. So another way you can say it is, for each number k, there's a fixed bound such that everybody will have been in the room at least k times by that number. Yes?
So could you just have the first person, like people just flipping the switch up, and then they start counting when, I know because you don't know if you're the first.
Right, so
You just choose a special.
Yeah.
we choose a special. Right, if you haven't seen the Lego movie, there's some really good speeches about the special. And I know, the Lego movie's trying to be politically correct, trying to make everybody feel good that everybody can be the special. No. I'm sorry, life is not like that. Not everybody is the special. Alright, some people are more, this is more like Animal Farm, some people are more special than others. It makes sense to discriminate, it makes sense to choose the special ahead of time. Why did I choose Jesse?
The TA.
He's the TA. Right, it's really easy. There's so many names to remember, I can just say the TA. Also, I like writing Jesse sees this. He's somehow appealing to me. That was the real reason. So what do we do now? Because we don't know the initial configuration. But we can choose Jesse to be the special.
Well, you'll probably have to go twice around.
You go twice around. So what you can now do is you can flip the switch from on to off twice, and no more than twice. And if you do it that way, we don't know how many times people came in before Jesse. Because the problem is, maybe Jesse is the second person and I came in first, and I saw the switch was on and I flip it down. Jesse doesn't know the initial configuration. So Jesse waits to move it up. And so we don't know necessarily who is going to have flipped it earlier. But if you force yourself to go through twice, alright, so I think this is enough time to spend on this riddle. This is a good one, there's a lot of good stuff going on here. I have a solution to this one written up that I will share with the class. But I just want to recap because there's a lot of great themes about this. The first is very similar to what we did in last class with the 1 over x plus 1 over y plus 1 over z equals 1 over 2008. Try to look at a simpler problem and build from that. What is a simpler problem? Well, what if you knew the initial configuration? What if you knew who was the first one in? Can you solve it in those situations? And usually one of two things will happen. Either it makes the problem easier and that becomes the building block to a solution, or it forces you to start concentrating on things that don't really matter and you go into this abyss and spiral. Right? If the second thing is happening, then after a while, put that away and try going back to the general case. It does sometimes hurt to try to look at a simpler case to build intuition. Not always, but it does sometimes hurt. It's the same thing as if you have multiple ways of doing an integral. Try doing it one way, and if it's not working, put that off to the side and try another way. And so for this problem, if we knew the initial configuration, if we knew who was going in first, the problem is a lot easier. Then once we solve that, then we can say, okay, well, is there any way that we can then generalize it so that we don't know what the initial configuration is and we don't know who the first person is? And if you break it up into a lot of smaller problems, it's often easier than trying to do the general problem initially. Okay, any other questions about this one? I like the moving it like 1/23 or something like that. The other possibility is we don't necessarily have to move it 1/23. It would be interesting if you could have different amounts of movement so that depending on where you are, there's a unique way to be there. If we know the switch initially starts either up or down, is there some way to choose the amount of movement so that if you see it's at a certain place, there's only one way it could be there? So lots of things for you to try to think about for generalizations. Remember, it would have to be such that you don't know initially which way the switch began. So you have to be able to figure it out by just looking. Okay, so we're down to the blue eyes, brown eyes, and mass extinction, and the grid where you remove dots or coins.
Mass extinction.
Mass extinction? Okay. Alright. How many people in this class have blue eyes, out of curiosity? Alright. So, I apologize for the way this problem is phrased. This is the canonical way the problem is phrased. Blue eyes is bad. And if you understand how that you have blue eyes, you just all of a sudden realize that life is not worth living, and you just decide to end it. So as soon as you know you have blue eyes, you will kill yourself. Okay? I do not support this view. I know plenty of people who have blue eyes for living productive lives. I know some people, not I know some people. And so we will just assume, for the sake of argument, I'm not going to change the phrasing. There's a lot of math problems where the phrasing is no longer politically correct. We will just use this. As an aside, there have been some really good psych studies about telling people you're in the good group, you're in the bad group. And it doesn't matter which group they're in, it just matters what group they're told they're in. And their performance changes. And they've done, I think they've done eye color, where they tell people that blue-eyed people are better at learning. And then a few weeks into it, they tell the kindergartners, oh, I'm sorry, it's the brown eyes, we got the report wrong, it's the brown eyes who are smarter. And it's amazing how people's performance track what their expectations are told to be. So here, if no blue-eyed, kill yourself. But just yourself, okay? You will not take out others, especially not brown-eyed people. But you will only kill yourself if you are positive that you have blue eyes. Okay? Now, this is a strange world where people with blue eyes die by their own hand. Not surprisingly, this land has other strange properties, such as there's no glass or any reflective surfaces. And it is considered the most impolite of impoliteness to discuss eye color in public. Okay? So, no reflective surfaces, no eye color conversations. So don't even think of asking somebody, what's my eye color? Not an acceptable question. Do I have to ask Jesse what eye color he has? No, why not? I can see it. So you can see everyone else's eye colors. See